Prasanna. I'm a statistician at Biostats department. Uh, are you able to see my screen? All right. So if you could see my screen, then if at least one of you can respond, then we can go ahead and start the session for the day. Can you hear me loud and clear? Yep. All right. So what? Thank you. So what the plan for the day is to take you through some of the ideas behind preparing data for the analysis. I'm sure most of you are in the final year and trying to work towards statistical analysis. So this presentation is just to kind of show certain things that would come quite handy when you're trying to approach statisticians with your
my father was right. It's getting dark.
I also request if there are people to kind of mute their speaker phones. We will take all the questions about the last like 10 minutes, 15 minutes around 5 o'clock. So, all right. So the first part of it is we will go through on why we should be looking at data preparation. What are the main some of the aspects that are related with problems in raw data, and as we get kind of identifying those problems, then we also look at what are the available solutions or some of the best practices that are associated with those problems. There are 5 or 6 major categories that are identified as sources of data problems. One is associated with the data structure. So as some of you might know, we expect the data set to follow in a particular pattern. So that's the first issue. Most of the data sets may not be formatted in that particular pattern. The second aspect is in terms of outliers, which are sources of errors in the data set. So if you don't screen for outliers, then there could be a problem in your further analysis. Similar to outliers, there could be also problems with missing data, right? So a lot of variables could have missing information. So that is another aspect that needs to be screened for when you're looking at your data. And then you also have qualitative variables. So as you might have some of the numeric variables in your data, likewise you might have also non-numeric variables. So how you handle those non-numeric variables would also contribute to having a clean data set. And the final part of it, and the most important part of having data set prepared for analysis, is the documentation part. We will see some of the routines that goes into documentation of a data set. So so this is the common workflow. So you have a usual raw data which you would have collected in your study using a questionnaire or a CRF, and that raw data goes into a software. Maybe you used an Excel or you used Epidata, whatever software that you used, and then that data set is being explored and processed, and that after that exploration we take it into a specialized statistical software like in SPSS to start with, or in some cases you would use other softwares like Stata or another like R or SAS, and the results from them would be kind of inputted in your thesis. If it is for your thesis, then it goes into your thesis. If it is for your paper, a manuscript, then it goes into your manuscript. So that is the general workflow, right? I'm sure all of you would be able to identify with the workflow. It starts with the raw data set, and then the final endpoint is that somehow we have to convert this raw data set into a thesis or a manuscript or a report that has some insights which will be useful. So the problem is when you have human or a technical error that goes into the raw data, then all of the further workflows get carries that error with it. So if your raw data is clean, if there is no issues with your raw data, then there is no problem further down the line. But if your raw data is going to be affected with errors, the possibility is that you could have human error where you made mistakes while you're trying to enter data. It could be a technical error where you have not made any error, but then the data, the source data that you have itself is erroneous, right? So when you have those errors built into the raw data, then sure that error is going to carry forward all the way to your report or thesis. So what we need to do is we need to kind of circle back in these initial steps, basically to identify what these possible human or technical errors could be in your data set, and then flag them and if you can actually clean them up. So that is the process, right? So if you could identify those errors right at the beginning itself, whether it is very less or you have quite a large number of errors, the errors that are influential or the errors that are not so important. But whatever they may be, if you could identify those errors, flag them, and then you have a way in which you can treat those errors, resulting in a clean data set, so that whatever analysis or explorations or statistical methods that you use results in more or less accurate results in valid and accurate reports. So that is why we are here. So we are very concerned about what we actually input into our statistical analysis, so that our output is as a reflection of whatever we are done with our input data set. So as I was telling you, we need to the statistical analysis. It requires clean data set. I'll in a minute explain about what we mean by clean data set. And once you have a clean data set, that kind of makes it ready for statistical analysis. So you might have in your thesis or in your workup, you might have a lot of raw data sets. So one of the first steps that you need to kind of get into is the process of cleaning. So if you look at an average analysis time, we spend a lot of time looking at uh, cleaning of the data set. And the errors are both actually structural, and also there could be some functional errors. And what, as I said, the first step would be to sort out these errors. So errors creep in because in the real world, data sets have these the features of the data sets have these is common. So one, it's noisy, which means that the variability is quite higher as against, if you have a simulated data set or if you have some artificial ones. So because the real world data, the data sets are quite noisy, and likewise the data sets are incomplete. Most of the times you would have a lot of missing values for so many different variables. And likewise, you might also have values that are inconsistent, right? So in a real world data set, you would find these three features to be more commonly present. So one of the thing is that we need to convert this real world data into an analysis data. So that part is what is called as data preparation. And I'm going to just take you through a few steps and see how you can go with it. So this process of making data suitable for analysis, that's what we're calling it as data preparation. So as it's very well known, if you have garbage in, then it's going to result in garbage out. It's called as GIGO. And we would like to resolve the issues right at the beginning, because once you move into the analysis, then it gets very difficult, because if you're going to find out something wrong with the data set right after you finish your analysis, then that's quite later stage. Then you have to start right from the beginning. You have to that will lead to quite a lot of time delay and also an effort. So as I said, some of the features of data, one is to ensure that the structure or the schema for data is kind of fits in with what is required by a statistical software. So at the end of the day, you would take all the data that has been collected, and that will be fed into a statistical software. So if the data format is not specific to that software, then you might have a problem in transporting the data to the statistical software. So that's first feature. The second one, you would like to have as minimal errors or outliers as possible, right? So that's a it's not just for the statistical analysis, but overall for your research purposes as well. You want to have as reliable or as valid data as possible. The third aspect of a clean data is in terms of missing values. You would like to have for each of the variables in your data set, you would like to have as complete information as to the extent possible. And the fourth part is in terms of the criteria that we use to select your research participants. Sometimes the data may or may not correspond to those criteria. Suppose if you're interested only in people, let's say between age group of 40 and 60, ideally the data set should correspond to only among those with age of 40 and 60, right? So if you have somebody who is beyond those age boundaries, then that does not correspond to your research database. And the last part is in terms of documentation, where if you have adequate description for all the information that goes into your data. So if you have taken care of these main aspects, then there's a high chance that your the data that you use for your statistical analysis will be clean and can be readily analyzable. So what does it take? Or what does it take from a researcher in terms of preparing a clean data set? Very minimum technical skills. If, you don't need to be a programmer or somebody like that. It doesn't. Basic Excel skills would do, and some basic understanding of data, and some good documentation skills. Like if you are somebody who's keen on recording things and putting information that could serve as a documentation, then that's all is required in terms of data preparation. But the benefits are quite a lot, because if you put in that kind of a minimal effort and in preparing the data, that's going to make the life much easier later down the line
is
when
full
you're
of delicious fruits.
analyzing or when you are looking at your results. So I'll just sidestepping a little bit. So you all would have had a questionnaire like that, which I showed up here, and the questionnaire will have a range of questions, a set of questions, and we call those questions as variables, right? Each of these questions is considered as a variable because the value is going to change from one patient to the other. We also call them the variables are also called as fields in the language of database. So each one of these questions or each one of these columns is considered as fields when you talk about database. And then once you fill up this form for a particular patient or a participant, then that's called as a record, right? So you have fields for each of these questions, and when you have a completed information on one particular form, then you call that as a record. And when you have like a set of records, like when you have, suppose if your study size is about 500 and you have completed 500 records, and that 500 records together is called as a database or a data set, right? So if you notice this form here, you would see that there are specific uh, type of variables, right? So you have few date variables as I blocked here, which takes its values as dates. You also have few variables which I marked up here as numeric variables, meaning the values that those variables take are numbers, like heart rate and blood pressure and respiratory rate and temperature and variables like that. Then you also have a huge proportion of variables which are non-numeric, in the sense they don't take numbers. Mostly some of them are binary, which is just an yes or no type of response for each of those questions. Like if you take either comorbidities or symptoms or signs. Then you also have those multiple categorical variables. If you take mental status, the response could be any one of those four categories, right? So a set of a questionnaire, a CRF would probably contain a combination of these different sets of variables. Some of them would be, a few of them mostly would be date variables. You have few numeric variables, the first class of variables, and then a few non-numeric variables. And if you look at non-numeric variables, there could be binary, which is just two responses, yes or no. We could also have multiple responses like this one here of mental status. So, as I said, the first part is in terms of making sure the data set looks adequate to be transported to a statistical software. So the expectation is that the data structure is rectangular. So you have columns which represent the variables, and then you have rows which takes each of those patients. So as it's shown in this slide, so you have these, each of these columns meant for a specific variable, and then each of these rows are meant for a specific patient, and all the data set is being put in one single sheet. What you have to note up is that the first row is meant for the variable names, and the first column in the data set is meant for the identifiers, right? So the first row and then the first column is kind of exclusively meant for identifiers. The row is for identifying patients, and each of these columns is meant for identifying the variables. A few comments in the data sheet. It's better not to combine variable types. Like as I said, suppose if you have a variable like duration, and then it's, let's say it's measured in minutes. One of the tendency is to have them together as 100 minutes or 20 minutes. But what happens when you do that is you kind of mix this number with a string, and that becomes a problem when you try to read up in a statistical software. So one caveat, do not combine variables. And the second caveat is that as much as possible, do not include any text variables. For example, suppose you have something like a comorbidity or symptoms, and you're going to record each of the symptoms. Instead of writing them as in words, it's better to always have them as a binary variable. Like I showed you in the previous slide with CRF form, keep each of those comorbidities or signs or symptoms as separate variables, and then you can have it as a binary variable. The third caveat is that in your data sheet, which you're planning to use for your analysis, do not have any graphs, charts, or any other notes which you would generally have it if it's your lab, right? So if the database is meant for analysis, and if you're going to use that for your results for your thesis, keep it as clean as possible. So that's the first thing. The structure of the data, make sure it follows these guidelines that I just mentioned to you. So you may not have noticed there are some of the common elements like variable name, which you saw in the first line of the data sheet. Each of the name could also have a label, which would add the description to that variable. If it's not a straightforward variable name like a gender, height, and you have written some kind of a very short variable name, and if that needs a label, then there is also an inbuilt label that goes into the variable name. And then you have a type of variable like we discussed. You have numeric variable, you also have non-numeric, a binary variable, and you have variables that are of date types. And the fourth and the most important part of our data set is the values that these variables actually hold. So it's the numeric variables would be taking up numbers, and you have non-numeric variables that would probably be coded in some values, and likewise you have those date variables. And that brings us to the value labels, where we try to represent each of those non-numeric variables in terms of codes. And together, these common elements is what actually makes up a database. So when you say a database, what we inherently mean is that you have these present. It may not be readily seen, but then somewhere in the database, these aspects, these elements are in it. So some best practices, these are very small details, but nevertheless they make a huge difference. Like for instance, how do you name variables? There are very specific guidelines so that it stays. If you follow these details, then it becomes more structured and standardized. For instance, like if you look at variable names, the suggestion is that you have one word. It's a short word. It's not more than a 10-character word. So if you have something like a body mass index, so it's not suggested to put such a long word as a variable name. And likewise, no special characters are allowed. It is just a string of alphabets. There is none of those special characters are allowed in defining a variable name. It usually starts with an alphabet and it's in the lowercase, right? So when you're trying to define your variable name, just keep these things so it becomes easier to go with it. The second aspect is, as I said, some of the variable names may not be standalone. You might need a description. So the description could be about some kind of definition of what it represents. It might include measurement units, especially if there is a problem in terms of if there is alternate ways of measuring something. So that would help not only in analysis of data, but also later on when you're trying to interpret your results. So the other this thing, when you're putting up your database, try and understand the major categories. There are many subcategories that are available, but at least the major categories of data types. So as I said, the first could be a text field. The text field would allow entry of any type. Like you can enter text, you can enter numbers, you can enter any special characters. So it does not have a restriction in terms of what it takes as its value, right? So most of the hospital IDs, we call them as strings because you can combine numbers with alphabets. Like zip codes, for instance, again, you can combine numbers and alphabets together. The suggestion is use as minimal as possible because it's quite difficult to analyze them. The second set of fields are called as numeric fields, and this is the major interest when it comes to statistical analysis because they are strictly numbers. You could have either integers, which are whole numbers, or you could have decimals, right? So in the number line or rational numbers. And if you have numeric fields, it's good to set some kind of an expectations for those fields. So you can say, okay, if the field is meant to capture age, you can keep that field open, which means any number can be entered within that field. Or you can define and say, well, in my studies, the age is supposed to be bounded between 30 and 50. So that is what the expected entry is supposed to be. And likewise, the third set of is called as non-numeric field or Boolean fields, where it takes about yes or no, true or false values. The important thing about these non-numeric fields is that if you're coding up, let's say you have 10 variables which are of Boolean nature, which are non-numeric fields, yes and no, be consistent with the coding scheme, scheme, where one would mean yes and then 0 would mean no. If you're going to code up in that way, then you kind of consistently use the same set of coding for the rest of the variables as well. And then the last type of variables are the date fields, right? And then that you can put date fields in so many different ways with month first and then days and then the year, or you can choose to represent them in different ways. But whichever way you choose, be consistent across all your data forms, right? So try and understand what are the major types of variables or types of data that is involved in a database. Uh, the other aspect is what I just discussed to you about in terms of coding variables. For a variable like gender, you can the values are males and females. Generally, we suggest to code up these categories. For instance, you will code up males as 1 and females in zeros. We call them as value labels or codes, right? So likewise, it may not be necessarily just two categories. You might have more than two categories as well. Like if you have a Likert scale, the responses are 3 or 4. It's never, sometimes, and often, and always. But then when you enter data, you enter the codes. Whenever is coded as 0, sometimes is coded as 1, often is coded as 2, and always is coded as 3. So now the first part we saw about the structure of the data. How do you set up the database? The next part of it is in terms of what goes into your data set, right? So as I said, the expectation is that if you keep as much as possible in terms of numbers, then it makes the analysis and the reporting part as easy as it gets. So the suggestion is to keep in your data sheet, keep only numbers to the extent possible. So that means what? You would remove the text. You would not have any symbols, and especially you would not have those strings like as I showed here. So if it's an income, if you're recording income, you would not have uh, the letters going along with the numbers, or if you won't have symbols going along with numbers, you try to code up whatever non-numeric variables that are available. And there could be other formats as well. You might have non-numeric variables, and when there is a non-numeric variable, you try and see if you can, as I said before, you can code those word categories. So if you have a non-numeric variable, make sure that you have appropriate codes that represent those categories. Sometimes if there are only few categories, the code becomes easier. Like if you just have 3 categories, then you can say 1, 2, and 3. But then the code designs could also be a problem when you have too many categories, right? So suppose if you have like 20 or 30 categories for a particular variable, then the design of code itself could be an issue. In that case, you need to actually think about it a little ahead of your data entry and spend some time on how you design those codes. The last part is on date variable. As I said, use a consistent format, and it's if you are entering in Excel, Excel is quite known for kind of mangling up the dates. So a couple of points on using numeric and non-numeric variables. In your data set, if you have a list of numeric variables, try to capture them as they are. One tendency is to divide the numeric variable into ranges and then represent them in intervals. Like as I shown in the example here, if age is one of the variables, the best way to capture age would be as it is, rather than grouping them in some age categories and then measuring it as a categorical variable. So if you have it essentially in a continuous or a numeric variable in your data, set, you tend to capture them as a continuous variable as well. The second point with the numeric variable is that have information on original variables. Sometimes you would have a derived variable taken from the original variables. Like for example, you take BMI, which would be derived from height and weight. So have these two original variables in your database. Do not take them out from your database because you have calculated BMI and you may not actually require height and weight. Right? Similarly for age, you might have taken date of birth and then you would have calculated age or you would have derived age, but do not remove the date of birth from the original the master data set. That's for the numeric variable. Likewise, for the non-numeric variable, use codes consistently. I said you would be using codes for all the categorical or non-numerical variables, but one of the often practice is that people kind of change the codes. So if for one variable S is coded as 1 and then no is coded as 0, and then you keep that as for all the binary variables. Don't shift between what what does 1 represent and what does 0 represent, right? And this, when you're entering, be careful, is not an alphabet O, it's actually 0. Uh, Likewise, as I said, when you have more than one response for a given variable, like if I'm asking about comorbidity, there could be multiple comorbidities present in a patient. Then don't enter them in one single field. Try to capture each one of those comorbidities as a separate field. Suppose if somebody comes with diabetes, hypertension, and cardiovascular disease, don't write them as like diabetes, comma, hypertension, comma, and cardiovascular disease. Instead, have them as 3 different variables and say whether diabetes is present, yes or no, hypertension present, yes or no, and then cardiovascular disease present, yes or no. So the third part is with the missing values, right? That's one of the cruciating part of data set is to have to deal with missing values, but it's quite common, right? So if you have a set of patients, a few variables could be missing for each of those patients, right? So what you it's a little difficult to understand why values could be missing for a few of patients and not for others, but it makes it it's important to kind of understand what's the mechanism. Why should values be missing? Is it a systematic thing where things are missing because of certain reasons, or is it just missing at random? You know, that's something which needs to be distinguished. If it's missing at random, then you know there are statistical methods that can actually take care of that kind of a missing pattern. But if there are specific reasons why there is a missing data, then it's good to know about what was the mechanism that led to the missing value. It could be so many different things where a patient simply didn't respond to a particular question. For instance, like if you asked about income and then someone didn't want to answer about income, you might have a missing value for income for that patient. And likewise, if the person is asking the question, the researcher for some instance thinks that income is not an important question, he or she may not actually ask that question to the patient. So then you would have missing information on that variable. So there could be few reasons, but it's kind of good to investigate what was the reason for missing, and try and distinguish from a value that is missing at random. So what we do if values are missing, one, plan in advance, like you can actually code up missing values. The general tendency is to leave it as blank. That's good if you're consistent. Or if you're coding it up as NA, which stands for not available, then you use consistently for each of your data entry. Sometimes people also use a large value. Like if you think none of your variables in the data set can take a value like 999, then you use 999 that could stand for a missing data, right? So main point is before you kind of pass over this data set for analysis, check for the missing values and see and confirm them. Whether they are truly missing, or is it something that was not included because you missed out, and then finalize the data after you assess the patterns or mechanism for missing values. The fourth issue is in terms of outliers. This is an interesting part in terms of looking at data sets, where you look for how plausible a particular value is. Suppose if you have a variable, let's say I plotted those variables here, and let's say the majority of the distribution is in the middle part, right? So those are called as inliers. They might have some errors, but it's kind of hard to kind of identify them. And then you have a cut point, right? So this is, you might ask me how do we get these cut points? But these cut points come from your prior expectations, your experience from the previous studies. Just for the fact that you're an expert in that particular field, might know the usual range for these particular variable is from A to B. So if you have a value which is less than this threshold, If you have a value which is above this threshold, then those are called as suspects, right? So you are a little worried about why these values are above or below the threshold. And then you also have a hard cut point where it's kind of quite impossible to observe a value like this. Like suppose if you have age as a variable and then you see something like 102 or 103, you're really worried whether this is a mistake or this is an error, or you want to go further down into finding out how did we arrive at this value, right? So then for each of those you have a step that is involved. So if it is above the hard cut point, then it's kind of obvious in terms of error. But if it is about a soft cut point, then you're trying to see what could be the reasons, and you try to examine and identify the values that actually lay outside those boundary ranges. So what defines these cut points is generally we take a mean, and then we go 2 standard deviations down and 2 standard deviations above, and those form the bounds for detecting outliers, right? So that's a standard one if the data follows a normal distribution. But sometimes it could be also other distribution. Then in that case, instead of using mean and standard deviations, you would use medians with the interquartile range, right? So that's an important step in trying to look at the plausibility of values in the data, because the main it's interesting, and also the main reason is these results could be dominated by outliers. So if you don't examine outliers, and if you have even few outliers in your data set, your data set could be your results could be kind of influenced by these few outliers, right? So it may not be like you might have one or two here, and let's say you have not examined it, and then you went ahead with the analysis, and the one or two observations here at the far extreme could drive potentially your main results. So that's why it's an interesting part where you need to actually spend some time going through your observation, just calculating some summary statistics and seeing if all values are you know uh, kind of behave as expected. So so as I said, so it could also kind of creep in due to various reasons. One could be human error. There are some examples like where 585, people could read it as yes 85, and 50 could be read as 50 and stuff like that, where those outliers could come because of you know human errors, and that's been found common. So if you have 100 fields in your data set, about 6 per 100 fields are the errors could be due to human mistakes. It could also be due to incorrect reporting, or it could be due to sampling bias. Sometimes, like you have made a mistake in selecting a particular participant who may not be eligible for the inclusion in your study, and that could reflect in that outlier, right? So if you by mistake you included a person who's not supposed to be included, and let's say he's a healthy person or he's extremely sick, and the values would definitely kind of be related to that condition. So that could be a reason for your outlying values. So those are all systematic errors, and then just a pure chance you could actually end up having an outlier, right? So uh, if it is normally distributed, so if you go by standard deviation, even after 3 standard deviation, there is still a chance for having a value that lies above 3 standard deviations, right? So just a pure chance, you would come across a value which stands quite far from the average uh, value. So so it's good to know what's the mechanism, whether it is due to some kind of errors that's crept into the system, or it is actually due to an inherent variability. And then you kind of flag them. If you identify a few outliers in your database, you flag them for further investigations, and then you have to make a decision in terms of what you are going to do with it. Are you going to include those outliers in your analysis, or you're going to drop them completely off and then have an analysis that excludes those outliers, right? So that those decisions have to be you need to make those decisions based on your examinations. The last part is with how do you make the data useful, right? So now you have the data set, you have followed all the points that I was just briefly mentioning to you about the structure, how do you enter, what do you put in your database, how do you codify, what do you deal with missing and outlying values. But then now the question is, okay, how would you share, or how do you make the information useful uh, in the long term, right? So one of the things that goes with it is this creation of metadata, which captures the contextual information about your data, right? So you have data, but the data does not tell about many other things that goes in the creation of the data set, right? So the metadata catalogs those key items, like who is the author of the data, and then when was it created, a small abstract about how and why the data was collected, and from whom, and what was the methods. Are there any specific criteria that were used in selection of samples? Most of the things you would see them in your protocol that you use for your study, but then in the metadata, they're all very brief and kind of summarized information, extremely simple and to the point. And then you also have a data dictionary that goes with the metadata, where you try and describe the items that are present in your data set, right? So when you have a metadata, it kind of increases the value of the data that you create from your research, both the usability and also in terms of aiding the interpretations. So this is an example of a data dictionary. So what we're trying to do here is we're trying to describe the contents of the database, like what the database actually holds, and the format and the structure of the database, right? So suppose if I have 8 columns in my Excel sheet, so I list down those 8 columns by the numbers, and I say variable ID is held in column 1, name is held in column 2, column 3 is gender or sex, column 4 is age, and the variable names are listed under each of those columns. And then, as I said, sometimes these names are intuitive, you don't need a label, but sometimes you might need a label. For example, if you use a very short name, and then you may understand what SMK stands for, but then somebody else who's looking at your data, or even you after a point in time later, may not be able to recall what SMK stands for, right? So you give a label for each one of those variables, and then you also add units. So for relevant variables, if there is a measurement unit involved, you make sure that that measurement unit is kind of listed in your data dictionary. And the fifth column is quite important one, where you say what are the expected values for the variables, right? So gender is just male and female. So those are the only 2 categories that you expect under gender. So if it's patient age, you expect the lower bound for age is 20 and the upper bound is to be 45. And likewise for height, you define certain bounds, certain boundaries or limits within which you expect uh, the values to lie, right? So this is quite an useful information, because as I said, if you're trying to run for outlier or plausibility check, then these ranges would be used to check against them. And then you also mentioned the next one, how do we code up these categories? Suppose if you are male and female, what was the numbers that were used to represent these categories? The last part is the missing values. So if you are left them as blank, the missing values, they mentioned they are left as blank. If you use NA, then you say all missing values are coded up as NA. If you use a specific category, then you say like here, you say it's 999 is used to represent any of the missing values. So when you put down a document like this which gives you information about the data set, then together with the data set, it becomes you can read into the database and understand quite better. So the last part is the storage. So now you have created, you followed the guidelines, and then you store the database, because it's a quite an important part, because there's a lot of chance for losing the data set after a while, right? So if you store it, it's it's highly likely that there are quite few instances where people actually lose data sets. So there are some pointers on how you can store them. How you can even name your database so that it's kind of easily retrievable. And in terms of storage, the general strategy is 3-2-1, where you make 3 copies of your raw data, 2 copies to be stored on the site in your laptop or in your drives with you, and 1 copy to be stored somewhere outside, so that the chance of data loss is kind of minimized. Otherwise, you might, I don't know, you might. We have had quite a few experience where people have lost the data set and then trying to find out from one to the other in terms of where the data set is actually residing. So that's the final part, where you start with a CRF or a questionnaire. You put them in a particular structure, which I told you about, rectangular with columns meant for variables and rows meant for ID. Enter mostly about 2 types of variables, numeric and non-numeric variables. If it's a non-numeric variables, you code them, and you have labels for those codes. Then you go and you go through the data set, checking for missing data, either by each of the variables, or you look through each of the subjects and see if there are any particular patterns. And then once you do the missing data, you check for outliers. You have those bounds, which are called as soft and hard. If it is within the soft bounds, then you kind of examine, and also if it is beyond the hard bounds, then you kind of recheck the values and have to make a decision in terms of whether you would include or not include. And then you put all this together and create a metadata document, and then all of this gets fed into the analysis, and then the analysis moves smoothly into your results generation. So to summarize, we need to have the step called as data preparation, because if you don't do that, then there's a high chance of having data that is unclean, and then leading into results that are not valid or not clear. It's better to do it right at the beginning rather than kind of iterating it over back and again multiple times. So you do it at the beginning of your data analysis, confirm the data, and once you confirm, kind of freeze, do not kind of work with the data set, and then kind of proceed to the data analysis. So we also discussed about some of the main points. We saw the structure that we discussed. We talked about variable types, classified as numeric and non-numeric types. We also looked at the importance of looking at missing data and examining outliers, and then having a documentation that kind of holds together the different elements of the data set. Right? So if you kind of consider the points that we just discussed, then and implement them in your data set. So what that means is you would have a data set that is well streamlined, which would make your life and your work kind of much easier with data analysis and with statisticians. In technical terms, it's called portability, where you can move your data from person to person and from place to place without much of difficulty or hassle. Right? So I'll stop here. We'll spend about 5 to 10 minutes. If there are any questions from any one of you, if there are any clarifications. Any questions? Can you explain once why not to combine variables? All right. See, one one aspect is so it's better not to combine variables. If you look here, the first type is of numbers, and second type is of text. When you combine these two things, it becomes a problem. It becomes a problem because if let's say I'm interested in calculating the average duration, right? So average duration, it would work if it is just numbers. Then I can calculate the average. But when it kind of combined with words, then this is taken together as a text variable, right? So if it's a text variable, then you won't be able to run any stats on those text variable, right? So that's why if you divide and make this as a separate numeric variable, and if you want to capture the unit of measurement, then you keep it as a separate variable in which you would say how the duration was measured. Which software would be best for data entry for dissertation, Excel or Epidata? So my thing would be Epidata, but again it depends on your specific study. Like if your study has only, let's say, 15 subjects and just 4 variables, then it doesn't make the the effort that you put in doesn't actually much of a sense to record 15 variables and then you have only about 5 or 6 variables, right? But on the other hand, if you have considerable amount of work, like you have like hundreds of patients to be captured and your CRF is quite extensive, it's about 2 to 3 pages of CRF, then it makes sense to actually get into Epidata for your entry. So just look at your CRF and your sample size, then you'll be able to kind of say, whether the database would be small or will it be moderate or will it be large. If it is moderate or large, then it's good to go for Epidata or any other database system. Why should age be considered as a continuous variable as opposed to a categorical variable? Right. So age inherently is a continuous variable, right? So if you measure age, it can take any value between its range. So if you say in your study you're going to include everybody from 0 to 15 years, then age can take any value within its range, right? So and it's good to capture it as it is rather than categorizing them as saying 0 to 5 years, 5 to 7 years, and 7 to 10 years. The reason being, like once you categorize them, you cannot go back to your original data. Right? You lose a lot of information when you categorize, when you group and make them into a grouped variable. Suppose if I say a person is between age group of 0 and 5, I lost that information of which age he exactly is, right? So I don't have that information once I categorize them. If I have them as continuous variable in the data set, then I have that, that information. I might, in my analysis, I might categorize, but I have not lost that original information that it had. That was the reason why we would like to have a numeric or a continuous variable as it is in the data set, but in the analysis you can plan and see if you want to categorize them. I was asking with respect to analysis. So even in analysis, the same thing works. Like if you're using it as a continuous variable, then you have more statistical power to capture if you're any difference if you're interested in. Right? Suppose if you want to look at the age differences between two groups, because you have more information in a continuous variable, like as I just said, you are more likely to find a difference statistically, right? So you more likely try and keep the variable as a continuous variable than as a categorical variable. But the other side of it, if you think a categorization of age is more clinically interpretable, then you would categorize age or any other variable and then do the analysis. Any other questions? All right. So if there are no other questions, then thank you so much for listening. I'll see you tomorrow. Thank you.